Hello and welcome back to this lecture course on noise control in mechanical systems with myself Professor Sneha Singh from IIT Roorkee, and we just covered a module on noise in mechanical systems. So, we covered what are the major noise sources in the different types of common industrial machineries, sources in some commonly found machineries, and then the types of noise typically present like the structure borne or the airborne noise, and what are the different means of controlling these types of noise, controlling methods that are typically applied in mechanical systems, and also the mechanism in through which the noise is typically generated in the common machineries, in the commonly found machineries. So, the previous lecture, the previous module was to give you an overview of what happens in the common mechanical systems or what happens in the common machineries, how is the noise created, how this noise is propagating, what kind of spectral and temporal content we usually find in the various mechanical parts and the various common mechanical machineries and subcomponents, and what could be the typical strategy to control these noises. Depending on how they are created and how they are propagating, you can devise the strategy for controlling these noise in the commonly found machineries and the mechanical systems. So, with this overview and with this generic knowledge about how noise is coming in the mechanical devices and how it can be controlled, this is the last module of this lecture series, and in this module we will do some case by case study. So, we will do the case study of some typical mechanical system, we will analyze what are the sources, how they are propagating and what are the typical measures applied to them. So, our case studies will be done to apply the knowledge gained in all the subsequent all the previous lectures, whatever knowledge has been gained till now in this particular course. Now, it is time to apply them to some real life mechanical systems and see how you can apply your knowledge and be able to better control the noise in such systems. So, here the first case study would be a passenger car, a very common mechanical system that is available, and a case study of how noise comes in the car and how it is controlled in a passenger car. And if time permits, we will just introduce the second case study, which is the case study of a passenger train. So, let us see. So, a quick summary, these are the various common mechanical systems that create noise. You have road vehicles, railways, HVAC systems, some construction activities, the wind turbines, vessels, drones, aircrafts, electric vehicles, various kind of, almost every mechanical machinery or mechanical system unfortunately is always a source of noise. So, for this kind of courses, let us consider some of the very common mechanical systems like the road vehicles, railways, HVAC systems and the construction activities, and one by one we will be taking up the case studies for these 4 types of mechanical systems. So, the very first case study is of a passenger car. You can see this is a passenger car. Now, what are the common methods or common kind of noise sources in this kind of passenger car? You can see that obviously if you open the bonnet, you can see the engine that is operating, the internal combustion engine is a major noise source, and usually as we have seen before, the engine noise is kind of low frequency tone with higher harmonics. Okay, the noise has got peaks which correspond to the multiples. The peaks, they are same as the rotational frequency of the engine. So, whatever is the RPM of the engine, based on that you can find out the frequency of the engine's operation, which would be the RPM of the engine divided by 60 will give you the number of cycles per second, and your sound waves will have the frequencies content having this fundamental frequency and its higher order harmonics, typically the engine noise. Then you have other sources, because it's a complex mechanical system, there are a lot of things inside a car. So the other very dominant noise source is the tire road interaction noise. You know, the tire, they are rolling over in this hard surface and they are creating the noise. Okay. So if you have seen, just an observation, that suppose when you are driving in the road, you hear more noise, especially coming from the tire, and when you are driving through a softer ground, you hear less sound from the tire. So obviously you can make a guess that the tire road noise must be dependent on the type of surfaces that are coming in contact. In this case, it is the rolling noise, and the surfaces coming in contact are the tire treads and the roadway on which the car is moving, and that is creating your rolling noise. Then the engine is operating and the exhaust is being emitted from the backside, from the tailpipe. This is also a very common noise source, and the content and the of it is very much similar to the engine noise. There is like a very strong correlation between the engine noise and the exhaust noise, because the exhaust is automatically being released in sync with the engine operation. Okay. In the combustion cycle, the combustion is happening and the exhaust gases are then being released in the exhaust cycle of the engine. So that is, this noise is very much in sync with the IC engine noise. Then you have various internal components. These days, you know, horns are becoming one of the major noise sources, especially in the busy streets, in the cities, etc. People are just honking, and this is becoming a very common nuisance and a very common noise source. There is yet another noise source. If you see, for example, suppose you are driving on a passenger car and at a very high speed, and you slightly open your windscreen or your window, the glass of your window down, you can see a lot of air passing and you can hear the noise of the air, okay, the air blowing over the car's body. That is your aerodynamic noise. Okay. It's a noise created by the means of the air flowing over the car's body, and the higher would be the speed of your car, the higher you can, the more noisier will this aerodynamic noise get. By the observation you can see, you know, the slowly moving vehicle, very slowly moving in a slow speed, you do not hear that. But for suppose you are going in a highway at the speed of more than 80 kilometers per hour, and you just open your window glass for a little bit, you will see the gush of air and the blowing of the wind that is creating a lot of noise. Then there are some other sources as well. Vehicles have their HVAC systems, but these are more secondary sources. They are not as dominant as these noise sources which are very common. The transmission system, the braking, the HVAC systems, even the embedded vehicle electronics these days, and various other auxiliary components are also secondary sources of noise. So already discussed in the engine noise, you have majorly, you know, it is because of the internal combustion system. The turbochargers are also used these days, which are once again, although the turbochargers are giving more power to the engine and they are making the car capable of driving in adverse conditions, but they are also creating more noise in their operation. Then the cooling fans that are being used to cool down the engine and support it, they are also becoming a source of noise. Exhaust, the gases that are escaping through the exhaust system obviously are the exhaust. The tire road interaction, as I told you, is the rolling noise. It is typically, you know, created because of the friction available between the tires and the road surface. This friction or resistance is creating the noise or the rolling noise. And the aerodynamic noise is when the air flowing through the vehicle body and its components, you can hear this wind gushing. So obviously this is like the fluid structure interaction noise, as this is aerodynamic noise, is a typical fluid structure interaction noise. So how do these noise vary with the vehicle conditions? The noises, they vary with the change in the vehicle conditions. One of the most common one being the speed of the vehicle. The speed of the vehicle determines which will be the more dominant noise. So for example, engine noise is mostly steady and it increases with speed, but increase is not as prominent. Okay, it increases slightly with the speed, the level increases with the speed, but increase in the level is not very prominent. Okay, almost constant with speed, and the same goes for the exhaust. It is very much in sync with whatever is happening in the engine. There is obviously a slight increase in the level with the increase in the speed, because you are increasing the speed, you are needing more power, the engine is working more, and hence slightly higher level of noise is created, but the increase is not as prominent with the vehicle speed. But these two noise sources here, sharp increase with, there is a sharp increase in the level, in the noise level, with the increase in the speed, vehicle speed or the car speed. Same happens for both these cases. There is a very sharp increase in the noise level with the increase in the vehicle speed. Okay. So, this shows, this is one of the graph from this particular source here from this book, and you can see what is there in case of passenger cars and then in the case of heavy vehicles. In the passenger cars, what you see is that these days the passenger cars, they are designed to go for a higher speed. So, what is happening is that this grey line is your engine noise, it is also increasing. So, for till this speed here, what you observe is, till this speed the engine noise is dominates till this speed, okay, till this zone, and then beyond that, from here onwards, in the higher speeds, what is happening is that the tire rolling noise dominates, because the increase in the tire road interaction noise or the rolling noise is much sharper and higher. So, only at low speeds engine noise is the dominant one, and then as the speed increases, the most dominant noise becomes this rolling noise or the tire road interaction noise. And the same thing can be observed for the heavy vehicles, where for a certain speed the engine noise is dominating. Here engine is dominant, and after this speed the rolling noise becomes dominant, becomes the most dominant one. What are some of the other factors affecting these noise levels? In case of engine, if you can think about it, it would be the engine's design. For any system, it would definitely boil down to how it is designed, what materials are used in making it, and what type of engine it is, whether it is a 2-stroke, 4-stroke, etc., whether it is spark ignition, compression ignition. So, what type of engine you are using, that will also decide what is the noise level, okay, and how engine is mounted and connected to the body and connected / fixed to the car. That will also decide what kind of engine noise will be there. So, all of this is going to decide the noise level from the engine. And in the exhaust, obviously the type of engine, because engine, the vehicle's operating condition also decides, condition, and the fuel you are using, fuel used, because the kind of exhaust gases they are creating. Suppose you are using more quieter fuels or more cleaner fuels, obviously there will be lesser emissions and lesser exhaust, whereas if you use the petroleum products, direct petroleum products, there will be more exhaust emissions and hence there would be more exhaust noise. So, all of this will decide your exhaust noise. Then the tailpipe design and the kind of silencer or muffler used in the tailpipe. All of this is going to decide what will be your type of exhaust noise. Then the tire road interaction noise, other than the vehicle speed, we already know that it sharply increases with the vehicle speed, but other than the vehicle speed, it is typically a rolling noise where one surface or one solid surface is rolling over another solid surface. So, the surface roughness of the tire and the surface roughness of the road on which it is moving is going to decide your tire road interaction noise, and the tire tread design and the tire material, the road material, all of this is going to decide your tire road interaction noise. Aerodynamic noise will depend upon the vehicle's outer body's design. Okay. So, what you see is that these days you can see, previously you had these kind of cars, like Jeep form of cars. Okay. And then these days you have these, more premium cars designed in this way. So, here this is, a streamlined design. So, what is happening is that here, the air is getting obstructed more, there is lot of obstructions in the air, and the aerodynamic noise, it rises up because of the lot of obstructions to the airflow that is being offered by this car. But if you have more streamlined flow, then the air can flow without getting turbulent over the car's body, and here the aerodynamic noise will be much lesser. And hence these days, especially, we are getting more streamlined body design for vehicles, the reason being to control the aerodynamic noise, so that the outer shape is able to offer as less resistance as possible to the streamlined flow of the air through the body of the car. Okay, so some of the measures that I used, the most common measure, and this is installed in every commercial passenger car. Every commercial passenger car these days has got silencers and mufflers. This shows the outer body of a muffler. You can call it silencer or you can call it muffler. So, and in the inside, as you can see, these are the perforated components. Then you have the Helmholtz resonator cavities, and based on these, perforations and resonance phenomenon, it is able to absorb the noise. So, the purpose is to absorb the noise and reduce the back pressure. Then you can replace, now you are getting, more quieter vehicles. Now the combustion engine is being replaced with motor. So, very long back when you had the vehicles that had external combustion engine, like some of the trains and the ships, they used to have external combustion engine that was way more noisier. So, from the external combustion engine technology, the mankind progressed into internal combustion engine technology, where the engine and its operation became internal and embedded within an enclosure, and hence it became quieter than the external combustion engine. And now from internal combustion engine, we are shifting into use of electrical motors and use of batteries to power our vehicles. These hybrid electric vehicles are way more quieter. So, we are doing here source modification. We are simply changing the source, creating the noise. We are replacing the engine with a quieter source, a mechanical source, to we are shifting into an electrical source. Then the tire designs, you can see the commercial advertisements of the various tires you can see, and the tire is like a very essential component. The design of the tire will decide how much, the rolling noise can be controlled. It can control the rolling noise or the tire interaction noise, it is the same thing. And then it also provides sturdiness to the vehicle and decides how much it is going to, what is the kind of speed it can attain in the different kind of terrains and the different kind of grounds and roads. Then the suspension system becomes a very important aspect. This typically is used as vibration isolation. Okay? It provides a vibration isolation. So, basically this is your inside cabin in which the person is sort of sitting, and then these are the outside structures of the vehicle. Okay. And then you have between the cabin and the chassis. So, you have suspension systems typically, you can find them typically between, first of all between the tire or the wheel system, I will just say, between the wheel system and the chassis or the body or the frame of the vehicle. So, chassis system, you will have a suspension. So, it curbs the vibrations that might be induced due to the road inputs or whatever. Suppose the road has got some bumps or roughness, that will induce vibration. Okay. So, we have a suspension system that is going to curb this vibration to reach from the wheels into the chassis. Okay. So, there will be that will be your first layer of suspension or vibration isolation. So, first layer of vibration isolators are between the wheel system and the chassis system. Then the second layer of the suspension system or the vibration isolation system is found between the chassis system and the inner cabin. So, ultimately by the time it reaches the passengers, the vibrations have dampened out, they have reduced a lot because they are going through two levels of suspension. Okay. There is a suspension between the wheel and the chassis, and then there is another suspension between the chassis and the cabin, and whatever road vibrations were causing, whatever road inputs were causing the vibrations, they are getting isolated and they are not able to reach, or they are almost getting stopped from reaching inside the cabin and causing discomfort or creating noise inside the cabin. Then these various isolation mounts that are used, the engine is typically now can be mounted using the isolation mount, so that the engine noise, which could be both airborne and structure borne. So, at least to control the structure borne component of the engine noise, you can use the isolation mounts. If you have any other part of the automotive that is creating a lot of noise, you have to make sure that the way through which it is mounted into the rest of the body, you have proper isolation on those mounts. Then active noise control has taken up a hit in the controlling the cabin noise inside the car, where the sensors installed inside the car to measure the noise level, and then you have the speaker systems inside the car, and the ANC system is directly in sync and connected with the speaker systems of the car, and it is playing the anti-phase noise to dim out all the low frequency noise inside the cabin. Then the windscreen these days are also designed so that they are more sturdier and they are able to block the aerodynamic noise. So, they can block the aerodynamic noise from entering into the cabin and causing discomfort to the driver and the passengers. Then use of materials like foam, rubber, fiberglass, all of this in the car panels, doors and the floors, they can all help in absorbing of the sound. Weather stripping is yet another means through which, although weather stripping, which is lining up, this shows the weather stripping. What is it? It was usually developed for using the car in colder countries and the rainy regions, where you line up all the doors and the windows, you are lining up with these sealing devices, and then when you close it, it becomes airtight sealing. Okay. So, you are airtight, the car becomes airtight and there is no gaps. So, this was done to avoid the harshness of the weather, to use the car in cold regions and in the rainy regions. You have these rubber tubes and gaskets which are helping to make an airtight seal when the doors and the windows are closed, and they also help in sealing and dimming out the tire road interaction noise and the aerodynamic noise from entering into the cabin. Okay. So, both the aerodynamic and the rolling noise gets controlled. Because of this airtight sealing that is provided using the weather strippers. Then we have the streamlined outer body design, which helps in controlling the aerodynamic noise. We have various vibration isolators in the engine mounting. So, the engine is mounted and that structure has vibration isolators. Then you can notice various kind of the premium cars, they have a lot of carpeting and lot of upholstery. These paddings and carpetings are there. All of this not only add to the comfort of the passengers, but they also help in dimming down the noise inside the car, because see, when you close the car, it becomes a closed indoor space, and within the closed indoor space it is a reverberant field, and in the reverberant field absorption becomes a good mechanism to control noise. So in the insides of the car, if you can line a lot of absorbing materials like these these kind of pads, these kind of carpets, etc. So if you line the inside body of the car with these absorbers, they are going to control the reflections and bring the noise level inside the car's cabin as down. So these kind of things help in controlling the reverberant field inside the cabin. They control reflections. And then engine is usually encapsulated, usually engines these days, they are under some boxed covering, and you open the box and then you can examine your engine. So they are now encapsulated. This again acts like an enclosure, the source enclosure. Okay, here the source enclosure principle is used, and here you have the absorption principle where reflections are controlled. Okay. So this closes the case study on the passenger cars. The next case study is on a passenger train, and these are the various sources. I think it would be better to do the case study of the passenger train as part of the next lecture. So thank you for listening.